Okay, so if you remember partial derivative, probably some of you, may not be all of you, but some of you talking about partial derivative earlier in the past courses. So what is a partial derivative? The quick review. Right? Um, when we're talking about now, the definition of partial derivative in this topic is I have a function f, and function f and depends on two dependent variables x and y, and I can just say I can say this function is equivalent to function z. So function which is x and y, or z variable x and y. Right? They have two variable x and y. So what happened really, the partial derivative is that what happened to x if y is fixed, right? And what happened
Yeah.
to y if x is fixed? And really this partial derivative is kind of the story about this matter. What's happened to x when y is fixed, and what happened to y when x is fixed? And really, if you want to write this definition, it's going to be writing if z, the function of x and y, then fxy is a partial derivative I'm going to use a different terminology. So fxy represent the partial derivative of x and y. We can also write them such as fx or fy. We can also write them just like fx or fy, and that's those kind of a standard abbreviation we use. If you want to write what is fx, what is fy, so let's talk about that, what exactly it means. We can write fx, and really what does that mean? You can also write that is this way. You can also write, is a partial derivative of x of a function when y is constant. So if you want to write this thing in a limit format, you can write limit h tends to 0 or approaching to 0, and I'm going to be adding x plus h while y is not going to change, minus the original function. Right? So really what does that mean? And divided by h, what does that mean here? If I have a function like, let's suppose this is a function fxy, and if you want to do this function partial derivative, so really what you're doing, you're coming to the point, let's suppose you're coming to the point, you are asking yourself what's going to happen to the function if only x is changing, which is this guy, y is not changing. So function is coming here at this point. Maybe I can call this point a. At this point you're saying function is only changing x, so really this guy is delta x. You can also say this delta x is h. So what you're doing, you're just basically asking yourself what's going to happen to this function if only x is changing, y is not changing. There's no y change, only x is changing, and that is what it means. Same thing you can do if the function is coming here. You say what's going to happen if y is changing only, x is not changing. So if function is going to be moving, in first case, function is moving from here to there. And in the second case, function actually is moving from, when y is changing, x is not changing, function is going to go from here to there, right? Because only y is changing. Okay, let's complete this standard form of partial derivative in the form of limit. So I'm going to write fy n equals to limit h approaching to 0 f, my original function is fxy, so I'm going to be just adding the h on the y segment, not the x. So I'm going to say y plus h minus original function. Right. Now if I want to write those things in an example, I'm going to be writing pretty much an example. And I'm going to be writing a function fxy equal to 3x minus x squared y squared plus 2x cubed y. Okay. And I'm asking, I need to calculate two things from this function. The first one is this. And the second one is this. Right? If I want to take the derivative, so basically here, I'm going to say is here, I'm going to treating, here is y is constant. And here I'm going to treating x is constant. So what I'm going to do here, if I'm going to take the derivative with respect to x, right, with respect to x, so really I'm writing like this is, I'm going to mention again, I'm going to take the derivative just like you take the derivative dx over dy. It means you're taking with respect to y. Sometimes you're writing dy equals to dx with respect to x. Same thing I'm writing here with respect to x. Function taking is with respect to x, so the y is constant. Okay, so let's complete this example so we can talk about some little bit on notations, how we writing these notations. So here I'm going to take this 3. So x is going to be 1, x derivative is 1, minus, here it's going to be applying the derivative, but y is constant, so the only variable is x. So I'm going to be writing here minus 2x, y cube is going to come, y squared is going to come as is. Then I'm going to say plus, take the derivative, y is a constant, so 3 times 2 is a 6x squared, 6x squared, and then y come as is. On this side, when I take with respect to y, the first term becomes 0. Okay, the whole 3x is constant, and the derivative of a constant is 0. Minus, now I'm going to be taking with respect to y, so it's going to be 2y, x squared is going to come as is. So 2y and x squared is going to come as is, plus 2, really 2x x cubed isn't going to be do anything. It's going to be leave as is because a constant, and the derivative of y is 1. So I'm going to write like this. Okay. Notation. Let's talk about notation. How can I write these things? Right now I write like this, and right now I write like fy. You can also write like this. It means I'm taking derivative of a function with respect to x. But since the partial derivative, I cannot call it derivative like I used to be calling. I have to call a little bit differently. And the different way you're writing, you're going to be making it this symbol. This symbol means partial derivative of f with respect to partial derivative of with respect to x. partial derivative of f with respect to x. This is how you write, right? So let's suppose if I have another function called zx, it means I'm writing like this. Whatever is written here is going to go in the denominator, right? And if I have another derivative written like this, so let's suppose zy, I'm going to be writing partial derivative of z with respect to y. If it's written like this, I'm going to be writing like this. These are the way you're writing the partial derivative notations. Let's take a look at another problem to elaborate more. I have a function close to x, exponential x squared y. That is my function. We need to find fx, fy, and evaluate fx and fy at, or you can just basically giving a point. So we need to calculate fx and fy at this point, 1 comma ln 2. This is a point. Okay, so let me do it. I'm going to say my fx equals to 1 dot ex squared y with respect to x. So this is my function plus product. I'm going to be writing this time x as is and take the derivative of this guy, e x squared y. Okay, here's a function. I'm going to take the derivative is going to be equal to 2x y e x squared y. That's my function. I'm going to take the partial derivative of y equals to, I'm going to writing the x-axis as is and take the derivative of the second term, which is going to be it's going to be, it's better to write like this, x dot x squared e x squared y. Okay, now if I want to substitute the value of fx at this point, I'm going to substitute is going to be everywhere wherever the 1 is. So 1, x is going to go to the 1, so it's going to be e to the power 1 dot ln 2, dot means product here at this time, plus 2 ln 2 e and then ln 2, right? There's a 1. I'm going to eliminate this 1 as well because they 1 have no meanings really. So I'm going to just write in ln 2. All I did, I just substitute the value of y ln 2 and x is 1. In the derivative here, I'm going to be writing fy and I can also write like this. Since these are the two, so the bases are same, I'm going to be just make the power or add on and e to the power x squared y. Now I'm going to be substitute the value 1 comma ln 2. So this one is equals to really is equals to 1 e to the power ln 2 and e to the power ln 2 means 2. So my answers are this one. Here I can do a little bit more work if I can a little bit more simplified. Maybe I can say here is 2 plus this one is also 2, right? This one is also 2. So 2 times 2 is going to be 4 and ln2. And that is my partial derivative of x function with respect to x. Let's take a look at another problem. Function fxy 2x minus 5y plus 3. Here I have to calculate find fx, xy and fy, xy. Take again same approach. We're gonna keep one at a constant at one time. So my f, x, and let me just write here. This means is taking the function derivative with respect to x. Just to remind you. And if I take the derivative, it's gonna be y is constant, so it's gonna be 2 minus 0 minus 0, plus 0. So the answer is 2. If I take the derivative of y function with respect to y, it means I'm writing like this, equals to, here my x is constant, so 0 minus 5 and plus 0. So the answer is minus 5. So those are my answers. Let's take a look at another problem. This time function is getting a little bit complicated than the previous one. So here I'm going to be taking the function is already given in z, so I'm writing this. And I'm going to take another one function with respect to y. When I take this one, is going to be 2x, and the y is going to be constant, plus 3y squared. And this x is going to go up, so it's going to be minus 1, and minus 1 is going to be divided, minus 1 is going to be minus 2. So really you're going to be bringing it down, writing x squared. When there's a minus sign, it's going to be transferred here. I'll be writing with minus sign here. Maybe we can also elaborate a little bit. If we can simplify this guy, and it's going to be 2 x squared y. And if I'm taking this gun, it's going to be, so x cubed minus 3 y cubed, and this 2 is going to be gone. Okay. The other side with respect to y, I'm going to keep the x is constant, is much simpler. So this time is going to be minus 2x squared. Where is my question? Minus x squared over 2y squared plus 6y divided by x. If I take the LCM or least common multiplier on both sides is going to be 12y cubed minus x cubed. I don't think so we can further simplify this. So pretty much this is what we got. While we're talking about this, let's talk about another thing in a partial derivative, and we call higher order derivative. Okay. So another topic we try to integrate into the same topic, we call them higher order partial derivative. And really this higher order partial derivative means is nothing, it's a simply same kind of bookkeeping. All you're doing is I have a function, right? And we are approaching to first derivative with respect to x, so maybe I can call it fx. And what does that mean? It means I'm going to take this function with respect to, I'm going to write, maybe I can write it means is this function this is what it means. So what I'm going to do, I'm going to be writing another function like this, another x. The second x means the same thing. I'm going to be taking this whole thing and taking another derivative. So I'm going to be writing this function. The first derivative is going to go this way, and the second partial derivative, this is going to be first one, and the second partial derivative I'm going to be writing right outside of this is going to be writing like this, outside the parentheses, and I'm going to be writing pretty much the same way I wrote the first one, like this. And that is the representation of the second x. And if you simplify it, it's going to be writing like this. Delta is square, then delta x square. You see, one is the first square coming inside this delta, the second square going outside of the x. It means both the delta x are same. So why not just square the both? It means just square on the both and the function. Right? You can also write like this. If somebody writing, there's a different way you can write it. This means if somebody writing like this means there's a square here. And if somebody is writing like this, it means this. The first starting with left, so the first derivative is inside parentheses. It should be with respect to y, and the second, sorry, my bad, is going to be inside. It's going to be this guy. So it's going to be writing like this, and the second derivative is going to be going here. Right. So really, how it grows like this is the first entity, and then that's the second entity. If you have a third entity, you can also add, which we don't want to deal with that, but you can write like this, x, x, x. It means you have to take the derivative 3 times. So this is the first, this is the second, and this is the third. Right? So you can write like this. Let's take a look, some examples. Let's take a look another problem. Fine. What was the question asking, Alexandra? What was the question, Alexandra, you asking? On the sheet it says when we're writing here, so this is the way I'm writing. Okay. I think this is what is written, right? fxy means you take the derivative with respect to x first, which is this, and the y is going to be going outside. Okay, and go back to this problem. Let's take a look another problem. So there's a problem for partial derivative for higher order. Fine. And we have a bunch of them, right? So fyy, fxy, and yx, pretty much all kind of combination for the function. The function is giving this 3xy squared. Okay, minus 2y plus 5x squared y squared. And here I'm going to be just writing the first one, fx, because fxx cannot be calculated, so I need fx, right? And I also need fy, right? I need two functions initially because everything, right? If you go to any function, the second derivative, we need two basic one. So the first fx is going to be here, the y is constant, so I'm going to be taking this one 3 y squared plus 10, this whole thing will be 0, 10, 10x y squared, and fy equals to, when x is constant, is going to be 6x y minus 2, and if I take with respect to y, is going to be same thing, 10 x y, but x is going to be stay with x squared because x is constant at this point. Okay, now I'm going to be calculating fxx, so taking the second partial derivative with respect to x, so it's going to be first term, the whole thing will be gone to 0, and it's going to be just 10 y squared. Remember, I'm taking this derivative with from here, not from the original function, from here. And the second one will be fyy. I'm taking the function with respect to here. So this one is going to be equal to 6x plus 0, 10, and x squared. Y becomes 1. Now if I'm going to take the partial derivative of x with respect to y, fxy, so I'm going to be taking again this function and take the derivative with respect to y. So this is going to be 6y, since I don't have any x here, and plus with respect to y is going to be 20xy. And if I want to calculate fyx, I'm going to be taking this function and take the derivative from here, which is going to be equals to 6y plus 20xy. Okay, that's pretty much what we have in the answer of this. Let's take a look another problem. Okay, a function is given. Okay, here we need to find out pretty much zx, zxx, zy, and zyy. Then also need to calculate zxy and zyx. So all the 6 possibility second order partial derivative or higher order partial derivative. So we're going to be talking about real quick. This is fairly simple. So we're going to take this with respect to x. This is going to be 4x cubed minus 6xy squared. And the third term will be 0. If I take the derivative of same term, second derivative with respect to x, this is going to be equal to 12x squared minus 6y squared. And if I take the again dz over dx, and if I want to take it partial derivative with respect to y, so I'm going to be taking this one from here and take with respect to y. So it's going to be 0, right? The first thing will be 0 minus 12 xy. Okay, let's go to the other side. Other side is dc or dy equal to, the first one will be 0, then minus 6x squared y plus 4y cubed. If I take the second partial or second order derivative for this, is going to be equal to minus 12 minus, not minus 12, it's going to be 6. It's going to be minus 6x squared plus 12y squared. If I take xy with respect to x and y, so I have to take from here and dz squared dy. Okay, you're always writing like this even you taking the xy. So I am taking this one is going to equal to, with respect to y, with respect to x, y is already taking, so it's going to be minus 12 xy. Okay, you can find any other combination if you want. You just keep taking the derivative. The only thing you have to pay attention is discipline, how you take the derivative. Okay, let's do another second partial derivative, higher order, but we're going to be doing with some number, putting some limits. Let's take a look at another problem. Here what we're introducing a new method of doing partial derivative with respect to certain points. So what we're going to do, we have a problem, have a function x, y, z. I have a function in 3 variable involved, and it's going to be giving this way, x cubed by 4 z5. I want to find the partial derivative of all 3 first partial order derivative on 3 different points. So first one, I'm going to be calculating this. Second one, I'm going to be calculating this. Right. And third one, I'm going to be calculating this. And it's going to be same process. You can write maybe another way. You can write like this, the way we used to write. You can write like this. Make sure the way it's written is not going to confuse you. There is a bunch of different ways partial derivative can be written. And if I take this partial derivative of these, is going to be equal to 3x squared. Y and z are constant, they're going to come as is. Here, it's going to be 4 respect to y, 4 x cube y cube c 5. The last one, which is with respect to z, is going to be 5 x cube y 4 c 4. Since the points are given, we can substitute the points if it's given and then find the values. Maybe you can write here 3 and 0, so everything becomes 0, right? Everything becomes 0, and I'm just going to be writing the first one so we can understand actually what I did here. But the answer is really 0. And here, if I substitute the value, again answer is 0. Here the answer is 0. Right? You substitute the value, everything multiply, and answer becomes 0. Okay, so these are the ways, you can substitute the value and find the derivative. Let's take a look at another problem. We were talking about higher order partial derivative. So let's take another example. The function is given c equals to x to the power 4 minus 2xy plus 3y cubed. Here I have to calculate this function with respect to x, dz with respect to y, delta square z with respect to the second order partial derivative with respect to x. Okay, and then I also need to calculate this one with respect to dx dy. We also need to calculate dy dx, and the last one but not the least one, we're going to be calculating second order partial derivative of y. These are the typical 6 way I can take the partial derivative of a function of two variable or dual variable. Okay, so let's start the first one. The first one, if I take with respect to x, going to be 3. So it's going to be 4x cubed. 4x cubed minus 2y. If I take with respect to y, it's going to be, first one will be 0 and then minus 2x plus 9y cubed. And it's going to be cube is going to be reduced 1 power is to square. The third one with respect to the higher order derivative with respect to x, so I'm going to take the first one and taking here is going to be 12 x squared. That's it. The other one minus 2y becomes 0 because they are considered as a constant this time, and the constant derivative is 0. Let's go to the other side. If I take the dx with respect to dy, so I'm going to be taking this one with respect to y, is going to be equal to minus 2. Right, pretty much with respect to y is going to be minus 2. The first one, derivative of 4x cubed, will be 0 because they consider it as a constant here. I'm going to be taking dy, which is this one, and taking the second order with respect to x. And it's going to be minus 2. That's it. The rest of the thing will become 0. Same thing here. I'm going to be taking with respect to y, which is this one, and taking the second order. So it's going to be 0 plus 18y. Let's take a look at another example. Let's take a look at another problem. Function z is given here. And I need to find the derivative at this point. This function also given in the shape. The shape is given. And shape look like it's a spherical ball, right? So it's going to be this kind of shape. We know that when we take the derivative with respect to x, for a function with respect to x, I'm really putting y is a constant. So if this is my y and this is my x, so really when I'm taking the function, I'm basically making a line which is going from here up, coming down here. Right? In this line, y is constant. Same thing if I want to make a line which is x is constant, is going to be look like pretty much a slice coming from this way to this way. And this line, x is constant. Right? So value of x from here to there is constant. Here to there, if I make the projection here to there is constant. Everywhere is constant. So I'm going to be taking, first I'm going to be the function derivative with respect to x equal to half 25 minus x squared minus y squared. Right? And half minus half plus 1, so it's going to be minus half. Then I'm going to take the derivative what is inside the parenthesis or inside the square root with respect to x. So first term 25 is constant, is 0, minus y is also 0. The only thing left over is minus 2x. I can also write this 2 to cancel. I can also write this minus x, or I'm going to take the square root of the denominator because since it has a minus sign, and I can write like this. And if I'm going to substitute the value of this at 3, 0, 4, I can write like this. T0 or Tx at this point, substituting the values, is going to be minus 3 or 25 minus 0 minus 4 square. And if I, do some math, it's going to be 9. So minus 3 and then it's going to be 3. 3 cancelling out, the answer will be minus 1. That is my answer for derivative of the function with respect to x. I'm going to do the same thing with respect to y. Going to be half. Exactly same methodology. This time I'm going to take the derivative. Everything will be 0. Just this guy to be minus 2y left over. I can also write like this, and 2 to cancel again. One more time is going to be minus y divided by square root of 25 minus 0 minus, minus x squared minus y squared. If I substitute the value, right, so the function C3 0 4 equals to, I substitute, everything becomes really 0 because I have a y here in the numerator, so it becomes, everything becomes 0, and that is my answer for this one. Really, these are the two slope of the line. So really the point is here. If I want to draw this point is supposed to look like here, and this minus 1 is a slope with respect to x, and 1 is a slope, 0 is a slope of respect to y for the function. Okay, so now let's take a look on all these partial derivative into going back and look into that. All the partial derivative we used to do it here right now, or we learned in our previous classes, they came from limit definition. So in this problem, we're going to be talking about this problem. We find partial derivative by using the limit definition right. So really, what does that mean? Just to remind, we learned about that partial derivative can also be writing in a limit form is limit delta x approaching to 0. We can also write like this, x plus delta x minus delta x y comma minus f xy over delta x. And I can also write the function partial derivative in a limit derivative form, delta y approaching to 0, and I can also write this time, I can write like this, y plus delta y minus the original function divided by delta y. If I want to solve a problem with this method, how can I do that? Okay, take a look at another example. Let's take a look at another problem. So here the problem is given, right? Fairly simple. I want to calculate this, and this, right? If I want to do it, my answer should be, with respect to x, should be 3, and the other one will be 2. But I don't want to do that. I want to use the limit theorem. So I'm going to be applying the limit theorem, and I'm going to beat this. So really, the way we're doing the partial derivative or doing a derivative is a shortcut. The actual methodology is the one I'm doing right now. You apply a limit where delta x approaches to 0, and then you're writing a function. And in this case, the function is 3, so I'm going to be just directly writing 3 x. So I'm going to be writing like this, 3 I'm going to replace this x with x plus delta x. So x plus delta x, and writing y as is, divided by minus my original function is this, right? Divided by my differential element, which is my delta x. So if I solve this one, it's going to be look like 3x and 3x. This guy and this guy going to be canceling out. This one and this one going to be canceling out. So what is left over? Left over is 3 delta x over delta x. And these are cancelling out, the answer 3. Same answer that would be usually got if I directly do the derivative, but that's a shortcut. This is the actual method. Let's to look at the other side. Other side will be limit of this is going to be limit y delta y approaching to 0 and it's going to be 3x plus 2y plus delta y minus my original function, which is 3x plus 2y, and then the denominator I have differential element, which is my delta y. If I do this side, it's going to be doing pretty much same thing. This one cancelling out, 2y, 2y cancelling out, and it's going to be left over 2 delta y over delta y, right? So I'm going to be writing the cancelling, and the answer is 2, which is again the same answer you can get by using drag method. That's what we are using all the time. So this is just another way you can do, partial derivative by using a differential form. The new topic I'm going to introduce is going to be called quotient rule. Yeah. So there is another rule we use, quotient rule, right? And quotient rule is really applied whenever you have a function in derivative, right? And for example, I'm going to be just telling you. So quotient rule are applied. When do we apply? Is to solve difficult equations or function when the dependent variable are involved in numerator and denominator both. For example, if I'm going to be giving you a problem like this, take this one, or the function is giving this. Do you really need to apply quotient rule here? And the answer is no. It's not too difficult because x, you want your variable is x and x is here, y is just a constant. So no, only x occur in the numerator. If I'm going to take a look on more, maybe let's take a look another problem. This one. Do I need to apply this quotient rule in this function? And the answer is yes. Why? Because we are taking derivative with respect to y, and y is involving in both numerator and denominator. So yes, y occurs in both the numerator, and denominator. Another one, if I gave you a function look like so the answer is no, because you only have y taking the derivative with respect to y, and y is only in the numerator, not in the denominator, so no. But if I change this same thing and writing like this, now the whole thing is completely changed because x is a variable and it's involving both in the numerator, so answer would be yes. You can apply the quotient rule. And what exactly the quotient rule is apply is not too complicated. For example, let me just do it. Let's take a look another problem. So we have problem is giving for example y equals to giving something look like this, and we need to find out y prime, which is really means with respect to x, right? We really asking to finding this. So can you apply quotient rule? Yes, because x is involved in both numerator and denominator. And how are you going to solve this guy? The rule is that you apply this prime equals to writing the numerator first. And the numerator is, sorry, the denominator first. The denominator is this. And then take the derivative of the numerator function, which is this. Then minus. Then writing the numerator as is. And take the derivative of the denominator, which is and divided by the whole thing with the square of the denominator. Okay, if I take this one, is going to be equals to squared plus 6 and 2x plus 1 x squared plus x minus 2 as is, and the derivative will be 3x squared. Thing is a cube. Yeah, this is a cube. No, this one should be square. And this one, yeah, square. So you're going to write like this and then divide it by. We can simplify this one, and simplification part is not too complicated. Depends on how complicated is the derivative. I can expand this one is going to be equals to 2x4 plus x cubed plus 12x plus 6 minus 3x4 plus 3x squared, sorry, cube minus 6x squared and divided by x plus 6x cubed plus 6 squared. Okay, so we can further simplify it. I think there is a many ways you can simplify this one, and that would be the answer. Let's take a look at another problem. We need to find a proof. We need to prove and what is our expression. Expression is given like this: plus y with respect to y x, everything should be equals to 0 if the function of given, the z is given like this, and that is my function. Okay, so we can apply quotient rule, and quotient rule is considered to be a shortcut of doing these kind of derivatives, partial derivative. So I need to find the derivative with respect to x, writing like this. So I'm going to take the numerator, which is with respect to x going to be 1, like x minus y. So if I take with respect to x, so x derivative is 1, minus y would be 0, so just 1 is left, and I'm going to be writing the numerator as is, then minus x plus y, and then derivative is 1 divided by the denominator is squared. Okay. We can simplify this one. It's going to be x, so this x and x is canceling out, and it's going to be left minus 2y or x minus y squared. If I do the same thing for my function with respect to y, is going to be not much different. It's going to be look like this: 1, and the numerator, sorry, the denominator is, I'm going to be writing like as is, minus, then I'm going to be writing the numerator as is, and take the derivative of the denominator, which is minus 1 at this point, and then writing the denominator with the square. If I'm going to simplify this, it's going to be look like this: x and x cancel. No, there is one minus, so minus minus x is not going to be cancelled. This minus is going to be make it this plus, so really y is going to be gone, and here is a 2x or x minus y to the power square. Now if you know, in our quotation we have the x and y, so if I'm going to be substituting this, it's going to be look like this. I can take the denominator is going to be I have to prove equals to 0, but if I'm writing this, it's going to be look like this. Minus 2xy plus 2xy divided by x minus y squared. So same thing is going to be, and whatever is written here, x minus y squared does not mean anything. Everything should be equal to 0. And we proved that our expression is valid by using quote and rule. Let's take a look at another problem. If z is given like this, find or you can call it, this one is, you can also call this cx, and you also need to find cxx. You also need to find cxy. We also need to find cy. We also need to find zyy. We also need to find zyx. Okay. Let's take a moment to write them one more time so we don't confuse. This one I can write like this. This one I can write like this. And really what it means, I can also write like this way, or I can also write more elaborating way. I can write, this is what it means. But usually we don't write like twice, we just make them square. This one is, we're going to be writing with dz taking derivative with respect to x, and then outside would be y, right? So that's why you're writing just like that. And remove this one. It's going to be y x. Okay. Same thing if I'm writing this one is done. I can write like this. And this one I can write okay, other way around. You notice one thing, whatever comes first here is this is my first derivative and it's going to grow on the second. Right? So you're taking the derivative of the first with y and then taking x. Right? That's how it grows. And that is how you're writing. So really you can see here, the way is going this way, the way it's going this way. They follow the same order. Y first and then x later. So y first and then x later. Right? It's a very important part, so we don't be confused. So let's solve this problem. I need to calculate all of these for this function. Okay, so writing here, it's going to be 2x and everything else will be 0. Then if I take the second derivative with respect to x, the answer would be just 2. X becomes 1. And if I take the second derivative of this with respect to y, the answer becomes 0. Same thing if I take the function of this with respect to y, the answer would be 6y. If I take this function with respect to y again, the answer would be 6. And if I take this function and take with respect to x, the answer would be 0. Okay. Thank you for watching Knowledge Academy. Please subscribe my channel.